So it's a great pleasure to introduce our first speaker, Nikolay Zheludev. He's a professor of physics at the University of Southampton in the UK, but he's also the deputy director of physics of the Optoelectronics Research Center at the University of Southampton. And he also directs the Center of Photonic Metamaterial in Southampton. And he's a founding director of the Center of Disruptive Photonics Technology at Nanyang Technical University in Singapore. And he's also the founding co-director of the Photonics Institute at the same university. Dr. Zheludev received his MS, PhD, and Doctor of Science from Moscow State University. And he joined the faculty at Southampton in 1991. He's won many awards, and I will mention a few. He's a senior research fellow for the Leverhulme Trust in 2001, senior research professorship at the UK Engineering and Physical Science Research Council in 2002. He won the Royal Society Wolfson Research Merit Award in 2009, the Thomas Young Medal of the IOP in 2015, and in 2018, he received the Nanyang Research Award. He's a fellow of the Royal Society of London, a fellow of the US National Academy of Engineering, the European Physical Society, and the Institute of Physics. And I'm sure I haven't captured everything in this. He's also the editor-in-chief of the Journal of Optics and advisor to the Nature Publishing Group. Actually, I apparently met, because we were just discussing this now, way back in the 1970s and 80s, Dr. Zheludev. But I remember especially a lecture he gave at PQE a few years ago. I think I will never forget it. And so I think you're in for a major treat to hear Dr. Zheludev talk about his research over the next 45 minutes. Nikolay, it's over to you.
Yeah, thank you. I'm about to share my screen, and let me do it properly, and then I will reply on that. I hope you see my screen right now, correct?
Yeah, we can see it well.
And I stopped sharing my video. Well, what I wanted to say is that this is really a very exciting opportunity and great pleasure to talk at this symposium. And I'm grateful to Professor Comcom and Boyd for inviting me. And I wanted to do a provocative talk, which I called Picophotonics. And Picophotonics is a subject which does not exist, but we believe that it will become a major subset of photonics in years to come. And I wanted to reassure you about that. So our group is mainly known for work on metamaterials, and we grew from the field of metamaterials. But we have become interested in phenomena which happens at a very small size scale. Oh, my computer doesn't change the slide.
Try using your arrows, your left and right arrows on your keypad.
Yeah. This is what I'm doing, and it does not react.
Okay. If you double click your screen, does that?
Yeah. Okay. This works. Yes. So I will provide a definition of picophotonics, which is a science of interactions of picometric scale objects and event with light. So we are talking about atomic scale events. So a hydrogen atom is about 30 picometers in diameter. The silicon atom is about 260 picometers in diameter. So I will give you today examples of what may become the field of picophotonics. So I will talk about Brownian movements and metamaterials and fluctuation of optical properties, which are related to them. I will talk about metamaterial functionalities, which are underpinned by small movements. I will talk about hyperspectral imaging of picometric movements in nanostructures. And I will tell you how, using light and artificial intelligence, one can measure a deeply sub-wavelength object, and in particular at picometric scales. So first of all, about Brownian movements in metamaterials. So these are examples of nanomechanical metamaterials. These metamaterials are now very popular in metamaterial community, and in optics, they are often made on very thin nanometric scale membranes of semiconductors, which are then decorated with dielectric or plasmonic metamolecules. And the beams of these metamolecules have freedom to move mutually because they are cut into beams, into strips. So this is a very interesting platform for achieving really exceptional functionality. So giant electro-optical and magneto-optical response has been demonstrated on these platforms. Giant optical nonlinearities, bistabilities, and new phenomena like nonlinear symmetric transmission. This platform works because it couples two systems. A photonic system, say based on plasmonic resonances, which helps to absorb light and emit light, and a mechanical system of the metamaterial, which is very, very highly nonlinear, much more nonlinear, if you wish, than the optical system. And this makes a great opportunity for photonics, which I will illustrate with one example later. So let us now look on what would happen if the metamaterial or any other nanostructure would have non-zero temperature. The first thing you will need to think about is Brownian motion. And this cartoon illustrates a very trivial Brownian motion of a nanocantilever in presence of gas. If you actually do your measurements in vacuum, you will need to think about a different source of Brownian motion. And this Brownian motion is related to the momentum transfer resulting from annihilation and creation of phonons, in this case of flexural phonons in the system. And this is the main mechanism of random motion of nanostructures. However, the question is that it's not always Brownian-like. It is not always random. If you take a look on such motion on a very fast time scale, you can see that the cantilever would move ballistically from one collision with phonon to another collision, to one act of annihilation and creation to another one. And between these movements, it will move in a ballistic fashion. And this is very important for functionality of high-speed devices, and I will come to discuss this later. I will start, however, with something more trivial. What thermal motion would mean for a metamaterial optical properties. So these meta elements in this metamaterials, so for instance, these beams of metamolecules can be described by a Langevin equation, which is essentially an equation of motion with random force on the right side. So if you analyze this mathematically, and this analysis is actually very accurate for these systems, you will see that the optical properties will depend on fluctuation of optical properties related to thermal fluctuation, will depend on optical properties of the material, and of course on the mechanical properties of the material. And if you put a typical characteristics of such metamaterial into the equations, you will see that at room temperature, at typical movements of the beams due to temperature is about 160, or let's say 100 picometers or so. And this results in change of optical properties in a scale of a fraction of percent, maybe up to 1% in certain resonance cases. So we have studied that. We wanted to understand the role of thermal motion. And how did we do that? So this is an example of building block of metamaterials. There are a couple of beams decorated with plasmonic structures. You essentially put them into a laser beam and measure the spectrum of transmitted radiation and the reflected radiation. You focus not on the optical part of the spectrum, but you focus on the acoustic part of the spectrum, because these beams oscillate with frequency of a few megahertz. And this diagram represents that, and you will see that on the natural frequency of oscillations of this beam, you will see that the spectral density of movements converted into spectral density of optical properties would have a peak, right? And this peak is a signature of thermal motion in metamaterial. And this thermal motion, as I said, is in scale of hundreds of picometers. So we optically can see 100 picometer movements pretty easy here. Very interesting feature is that such a beam being excited by a beam of light will absorb radiation, will increase the temperature, and the result of that, the stress in the beam will change, and the resonance frequency, this frequency, will drift depending on the intensity of laser you use. It will drift towards red part of the spectrum. It become smaller with high intensity. This is actually very important because it will illustrate a device application. So can we think of functionalities underpinned by very small movements? And indeed we do, and we have been looking at that for quite a while now, and I give you only one example from very recent results from our group. Think again of a beam forming the metamaterial. In classical mechanics, it is a very well-known fact that if you deflect this beam on a distance equal to its thickness, the response of the system becomes nonlinear. And as I said, this beam is well presented by an oscillator model, and you get an oscillator behavior in a nonlinear regime. And perhaps many of you have seen this curve, what happened in the oscillator nonlinear regime. And of course, you all know that this curve doesn't happen, and this is not what you see. Instead, you see a hysteresis when you change the driving frequency and the bistability resulting from that. And this, again, so here we are talking about mechanical part of the metamaterial, but it has implications for the optics because mutual movements of the beams are resulted in repositioning of these decorating elements made out of plasmonic metals, and as a result of that, optical properties change. So we have a system in which inheritedly has a capability of demonstrate bistability. And this is exactly what happens. So this now reflectivity in the optical part of the spectrum, we are talking about a telecom frequency 1.3 microns. So you now oscillate your metamaterial, you put it on a shaker and oscillate on a frequency around 2 megahertz. If you drive the frequency up and then down, you see a hysteresis in optical properties. But this is a hysteresis which is driven by external shaker. Can we achieve the same by light? And of course, you can do exactly the same with light. If you change the optical power, you will recover very, very similar hysteresis behavior. So in the first case, you were changing the driving frequency of the external force, so this mechanical oscillator. And in this case, when you act optically, you change the fundamental, the natural frequency of oscillator itself, because as I already said, the fundamental frequency, the natural frequency of oscillator depends on the laser power. So this is one example. So we have become interested in exactly studying small movements in photonic nanostructure, and have developed a technique which allows mapping such movements. So I will explain very briefly how it works. So pretend you have a scanning electron microscope, a conventional scanning electron microscope, and you observe a bee which has moving wings, right? So in a conventional microscope, you will get a static image. What we do a slightly different. We fix the electron beam position at a particular point, and then detect secondary electrons and measure the spectrum of secondary electron movements. As a result of that, we can create an image of mechanical movements at a given frequency. And remarkably, that these measurements can be done with incredible sensitivity. So we can detect amplitudes of displacement at a given frequency in a scale of picometers, only within a second of observations. Why it is possible is because when you fire electron beam at a, say, again, at a cantilever, and cantilever has a sharp edge. So the signal, the variation of the signal resulted from movements of the cantilever are proportional to the gradient of the cantilever. So for a very sharp atomic scale cantilever, you can have a very, very sharp gradient. And also, of course, displacement plays a role here, and the diameter of the beam. But altogether, in a conventional microscope, will give you 1 picometer in the second of observation, which is limited by the short noise of your electron beam only. Okay, so these are now representative examples of metamaterials, which we shake by a piezo driver at a given frequency, and we tune the frequency to highlight a certain resonance mode in the structure. So at 1.45 megahertz, we highlight this one, or that one, or two of them. And this is all imaged by this technique, which recovers hyperspectral images of the object with this technique. So we did a silly demonstration recreating a famous image of a flea by Robert Hooke by now hyperspectrally. When we shake flea, this is actually a flea, a real flea which was murdered and then put in electron microscope. And we can see movements at certain frequencies of the satire of this flea. Okay, but this is sort of quite far from fundamental physics, but you can do with this technique some very interesting fundamental physics experiments. For instance, if you have a cantilever, you put your beam of electrons here, you can trace the position of the cantilever with very good resolution. And this is a function of time. So this is a thermal motion of the cantilever. And this thermal motion would have the spectrum, which represents the fundamental frequency of the cantilever and some other modes of motion. What is important is that you can now statistically analyze this dependence of the position on time. And the statistics here gives you opportunity to analyze this in terms of measured square displacement of the cantilever end as a function of the observation time. And you can see that when your observation time is short, so certainly shorter than 10⁻⁵ seconds, So the average displacement goes with time, proportionally with time. So this is that ballistic regime I was talking about. So in this regime, you can actually recover the actual velocity of movements of the cantilever. When you go further and your observation time become longer, the cantilever starts showing diffusive regime of behavior. And then when you go to even further, you start see bound oscillation of the cantilever. But important thing, you actually can see the ballistic regime. This is also maybe illustrated by looking at the normalized velocity of the correlation function. So within very short period, you measure velocity, and you measure velocity after this period, it is the same. So it brings quite interesting opportunity for studying dynamics of non-mechanical switching. It has application in ultra-fast thermometry, mass measurements, and foundation of thermodynamics. But I promised you a Picophotonics talk, and essentially my challenge is, can we do similar things all optically without electron beams? And I will lead you to that in the talk. Well, first of all, I will talk about measuring deeply subwavelength object with help of artificial intelligence. Why it is important? It's important is that for the following reasons. So any act of imaging is solving ill-posed inverse light scattering problem. And what has been understood actually quite a few years ago, but only became important right now when experiments, we start doing the experiments, is that the problem of inverse scattering may be reduced to solving the Fredholm integral equation. And what mathematicians understood is that Fredholm integral equation can actually be accurately solved by fully connected neural networks. So we come to artificial intelligence. And through, through that, the diffraction limit of conventional optical microscope may be surpassed several times over. In fact, several orders over. So how do we do that? This is a recently published experiment, perhaps most advanced so far in this field. So what you do, you put a slit, a hole in a metal screen, illuminate it with plane wave, and then detect diffraction pattern. And diffraction pattern looks like that, right? So in more detail, this is a diffraction pattern. So what you then do, you create a large number of slits with a variety of sizes, all in deeply sub-wavelength scale, certainly smaller than half wavelengths of light in width. And you detect a number of diffraction pattern and provide information on the diffraction pattern and the slit width to a convolutional neural network, which is trained through this process. When it's trained, and you do not need many, you need about 100 slits to get impressive results. You then show this instrument an unknown slit, and this will, through a function of the neural network, you will get the width of the slit. And I will show how well it works. So this is how well it works. So the optically measured width of slit and measure it through electron microscope. If you only care about intensity of light passing through, so the bigger the hole get better intensity. The results are good, not as good. But if you analyze the entire diffraction pattern, the resolution in becoming about lambda by 100. And this is with very small training set. And as you perhaps know, in deep learning, the performance of the recovery process goes with the size of the training set. But even with this training set, I observe and sort of trying to bring your attention to the fact that we can challenge accuracy of the conventional electron microscope or accuracy of fabrication of focused ion beam, which was used to make the slits. And this analysis, I don't want to spend much time on analysis of that, could be done within this instrument. You can simultaneously assess the FIB accuracy and accuracy of scanning electron microscope. And they, as you can see here, they're in the same ballpark. Scanning electron microscope does not much better job than optics to measure the size of the slit. And this is in a very trivial single shot experiment. So now I will go to imaging and metrology with topologically structured light. And I think this is really important because this indeed will bring us to the picometric scales. So far, accuracy of this method was a few nanometers. I just described it. Can we do better? And I will briefly show you something, how we can get to the ideas which we're exploring now with reference to our prior work in this field. So to explain that, I need to say a few words about something which is in optics is known now as super oscillation. This is super oscillations is a concept which was first introduced by Akira Aronov and later by Michael Berry, applied to optics. But nevertheless, it's about special functions. So there are special functions, which a class of functions, which have the following property. They have a limited spectrum, completely limited spectrum, but in certain areas of the function, they can oscillate faster than the highest harmonic in the spectrum. And this is an example of a function with appropriate coefficients. It will give you these oscillating curves. In the middle of the function, in this area, there will be a very fast section of this function, which oscillates much faster than the highest harmonics. This is possible because in the entire function, the high frequency components will cancel each other, which do not cancel in the small section of the function. So as Michael Berry at some stage wrote, in the Wigner representation of the local Fourier spectrum can have both positive and negative values, which cause substantial cancellation in the Fourier spectrum of the entire function. For optics, this means a very simple thing. You can focus light by interference of coherent beams into a small spot of any size. And the only and most important price to pay for that is that the spot size may be arbitrarily small, but energy going into this spot size polynomially goes down. Nevertheless, we were excited by this idea, and it all started with observing these hotspots in array through diffraction on the array of quasi-crystal arrays of holes, and then showing that this super oscillatory hotspot can actually be imaged by a conventional lens because they're free space waves, and free space waves can be imaged by conventional optics, so you can actually photograph them. And then we have developed at a later stage an instructive algorithm on how to create a mask, optical mask with variable phase retardation and density, which will create your hotspot of any diameter and any size and any profile. But this was then a way we entered microscopy with such hotspots. And here I show you an example of such a microscope. So this is a mask which creates super oscillatory field, which has a small hotspot and then you put it in a confocal arrangement. And this in confocal arrangement, you scan your hotspot through the image, and then you collect it from the aperture and build the image like in a conventional confocal microscope, with the difference that illuminating hotspot is very, very small. So it's certainly some diffraction. And this has become a routine technique for microscopy. Nevertheless, it was difficult to get further than lambda by 6, lambda by 5, because, as I said, energy going into hotspot rapidly decreases, and you need to phase the signal-to-noise ratio. So nevertheless, this technology has been advanced to the stage when we have been able to image biological samples. These are examples of looking at stem cells and their propagation on the surfaces, and compare this with other techniques. But this is still, this has been a very exciting journey for us. But we found very, very soon that we sort of hardly can go practically beyond lambda by 5, lambda by 6. And this is not atomic scale yet. And this is not what I promised at the beginning. And now I'm going to tell you how you can go further than lambda by 5 or lambda by 6 in a practical microscope arrangement. So in order to tell that, I need to go back to the complex electromagnetic field. So these are pictures which I imported with some modifications from Michael Berry's paper, where he simply analyzed what would happen if you take about 50 beams, all coherent, but randomly directed, interfering in free space. And you will see that there will be singularities in the resulting field. There will be zones, this yellow zones, of where the local K vector, that is gradient of phase of the field, is higher than the gradient of the, is higher than the K vector of the plane wave. And there will be areas in which actually energy, this pink areas, in where energy actually goes back. They're called so backflow zones. So this is the typical characteristics of any complex electromagnetic field, which is made of coherent plane waves. So what we decided to start with, we decided to make experimental observation of these small features. As you can see, these features are typically much smaller than the wavelengths of light. And we have become interested in this structuring of this electromagnetic field. So, it's a long story. I will tell you only a few words about that. You create a metasurface, this metasurface, which simultaneously generate two fields. In one polarization, a plane wave. In another polarization, a structured field. So this is one polarization, structured field, plane wave. And you can do it, you can engineer such field as you please. In particular, you can create superoscillatory field or any topologically structured field. And then you do interferometry using polarization filters. And through this interferometry, you can completely recover the structure of the electromagnetic field. So these are examples, I will show you very briefly. These are examples of the intensity profile of superoscillatory Fochy, a very typical situation of singularities, and areas of high local K vectors, that is gradient of the phase in this direction. And there will be in this field areas of energy backflow. The interesting thing that even in a very simple topologically structured field, you will have areas which are much, much smaller than wavelengths of light. So obviously the singularity has zero size itself, but even area where K vector exceeds the K vector of free space is roughly 1% of the wavelength. The areas which have energy backflow is about 5% of wavelength. And we start thinking, can we use that for something useful. So if we can structure light deeply below sub-wavelength scale, can we have some useful application of that? And we actually, the first thing which we did, we took advantage of high localization of local K vector. So as our interferometry allows us to recover this K vector maps, we compare this K vector maps with the intensity map of the beam. And you can see intensity map has much broader distribution than K vector maps. As I said, about 100 times broader. So we developed a technique which we called optical ruler metrology. In conventional metrology, you take a lens and look on your ruler, and you move lens against the ruler and read the divisions. And here, lambda by 2 is your limit. However, if you, instead of a conventional ruler, use optical ruler, a metamaterial which creates this structured fields, you can use this elements of the structured fields, in this case, area of high values of local wave vector, as bars of the ruler, which are much smaller than lambda by 2. And this this allows us to very simply demonstrate a metrology in which one measure displacement of platform A against a platform B, simply looking at this very narrow localization of energy. And in a very simple setup, you immediately can get displacement resolution of about 1 nanometer, maybe slightly less. Okay, but so this was great, and this there was a considerable interest to this idea. But we thought, can we now go from metrology to imaging? And we call it now deeply sub-wavelength topological microscopy and metrology. This indeed seems to be getting us to picometric level of resolution. What the idea is? Say this is the object we want to measure. We want to image, if you wish. What we do, we put it into a highly structured field. And then we move it in this field in such a way that it moves across singularities, energy backflow areas, and various peculiarities of this field, which are deeply sub-wavelength. And we hope that as a result of this movement of this object in this field, the scattering of light will change dramatically when a singularity, for instance, of the optical field will meet a small feature of the object. And when you move it from this position, the scattering will change. And this is actually indeed what is happening. So this is just computer illustration of that. This is singular map of a particular field, which has this intensity and this phase. You now put here a nanoparticle, which is lambda by 1,000 in size, and you move it across, right? So you simply pass this structure, passing singularity points. And what I plot here is a diffraction pattern. This is position on the diffraction on the detector, seeing the diffraction pattern. And I plotted here change of scattered light, which is caused by presence of particle and by displacement of the particle on lambda by 2000. And you see that these are dramatic changes. But can we use this for imaging? So the idea of using this for imaging is again based on artificial intelligence. And I already introduced some trivial version of that. Now what you have to do, if you want to image a flea or a bee here, you create a topologically structured light. You then scan your beam across this object. So hoping that topological feature of light will meet features of your object, and you measure diffraction pattern, and you do it for a large number of similar objects. And this would create a training set for deep learning process. And then once it's properly trained, you will be able to recover parameters of your unknown object. And we have shown, and this is an illustration, that with making this scanning more and more accurate, you actually indeed increase resolution of the technique. And at that stage, I will show you perhaps the most recent results, which we are very proud of, and which illustrate that through this idea, you actually can get to very good level of resolution. So the idea is as follows. The main problem with artificial intelligence always, whatever you do, is to create a trustworthy and nice training set. And we decided to focus at the beginning at a very fundamental problem, to measure position of a nanowire in the gap, right? So nanowire, this is the body of the gap, and then the nanowire is moving inside the gap. And we would like to measure the size of this gap, that is the position of the nanowire. We use exactly the same technique. We use illumination, we make diffraction pattern, but now we have opportunity to control the position of nanowire at will electrostatically. You simply apply electrostatic voltage between the nanowire and the sides of the gap, and you can control this movement. As a result of that, you can get a training set of incredible accuracy, and which is congruent with the optical system. So you train your system on the same sample which you will be measuring. So then you create as many positions of the nanowire as possible. You train your convolutional neural network, then you show them unknown size of the unknown position of the wire, and will give you output position. So this actually works extremely well. And what is important here is the use of deep learning. If you use deep learning and do it properly, you actually are completely free from all the problems related, for instance, to the mechanical instability of the system, to vibration on the optical table, to anything, because diffraction pattern will be shaken, but the structure of diffraction pattern will not. And this is what you would want to achieve. So this is a result of measuring the nanowire with plane wave illumination. You can see that I plotted here displacement as it physically was and optically measured displacement. And you see that at large displacements of about 1 to 10 nanometer, it's really a very well correlated dependence, and then it becomes fuzzy, and at about 400 nanometers, you are losing accuracy of the system. So the accuracy here is about 400 nanometers, which is already, excuse me, I said 400 nanometers. Oh, sorry. This is 400 picometers. So this is about this position. Sorry about that. It's my slide mistake. So we get to the accuracy of about 400 picometers. So which is all the picometric. But if you do exactly the same thing with topologically structured light, you will see that your performance of your device improves dramatically. From 400 picometers, it got to about 50 picometers. And you can see that this correlation between actually measured and physical displacement become a nicer curve and goes to about this position of 50 picometers of accuracy. So therefore, again, sort of look, this is an optical measurement process which is a single shot measurement. You only need to detect one thing, a diffraction pattern, and it will give you information about the size of the gap with picometric accuracy. Now you can challenge me with saying, okay, but this beam by thermal motion would move 100 picometers. So what does it mean that you can measure 50 picometers movement? It means that we actually measure a time average. So actual position of the beam is, I picture it here with this blue vibrating line. But the mechanical damping time of Brownian motion is about 3 microseconds. But the integration time of our detector is about 130 microseconds. So we integrate with the thermal motion of the system. And when we will go further and further along this line, this will be a bigger and bigger problem. And so we essentially measuring average positions of the nano object. Okay, why does it work so well? And this is really my concluding slide. The deep learning process, based on a large training set, provides, as I said, accurate deconvolution mechanism, which is mathematically proven. Of course, we are so far working with objects which have considerable sparsity, and we actually know about the object. It does also help in running the neural network efficiently. But from the perspective of the information theory, the multiple scattering patterns, which we analyze before measurements, provides much more information than single shot over measurements by CCD array coming from a lens. So we exploit much more information. And of course, when it comes to topological illumination, with the fields which has very high values of K vectors, we enjoy that, and topological illumination ensure presence of high wave vectors. That of course helps the see small features of the object. So this is my last slide. This is, you know what is that? I will not say what is that. You know this anyway, right? So this something is about 100 nanometers in diameter. It has spikes which are about 20 nanometers long. This spike oscillates at about gigahertz frequency. And what I'm really saying is that using this sort of approaches based on artificial intelligence and topological light, topological structured light, we can measure all of that optically. We can find the virus shape and size. We can find the spike length. We can measure oscillation frequency, and we are busy trying to demonstrate that. And my very last slide is, I could not resist that everybody read the Plenty of Room at the Bottom by Richard Feynman. But and he was talking actually about electron microscope, but the narrative is very much the same. He said, we shall try to improve microscopes 100 times over, right, beyond the diffraction limit. And he said, we know that there are theorems which prove that this is impossible. And numerical aperture is a problem. And this makes a limit of a half wavelength. But every theorem, there are assumptions. And I think I tried to demonstrate that really using different approaches and different information flow, we can get much further, much further than the diffraction limit. And of course, this, as Richard Feynman said, we should use mathematics to help us with that. That's all. So optical detection of Brownian motion of about 100 picometers is very easy to achieve. We can, with electron beams, measure amplitudes of displacement about 1 picometer. We can do optical measurements with without topologically structured light at about lambda by 100, lambda by 200. And if we use topologically structured light, we already demonstrated 50 picometers resolution, which is bigger than the size of the hydrogen atom. Oh, sorry, which is bigger, but not much bigger, only factor of 2, and smaller than the size of the silicon from which this beam is made. So I want to give a credit to a great group of people at Southampton and at NTU Singapore. And I would like to thank you for listening to me. Thank you very much. I'm done.
Thank you very much, Professor Zheludev. We have a few questions in the Q&A section. Paul, would you like me to go ahead with those?
Yes, please do. Please.
Okay. The first question is, the super oscillations look like limit cycles in phase space. Are they related?
I cannot answer this question because I don't know what are limit cycles in free space.
In phase space.
In phase space. I simply don't know that.
Okay.
But I do know that maybe I can help with finding answers to this question. We just have written a big review for Nature Review Physics, which has an extensive literature, nearly 200 papers, everything which has been published on super oscillation so far, including mathematics of them. This paper shall be out at the end of next week. And so I hope this will provide necessary base for answering this question.
Hopefully, yes. I can move on to the next question then. Do the vector properties of the light field play a role in the excitation of the modes of the cantilever type mechanical oscillator?
Yes, yes, they do. However, experiments which we performed so far, essentially you may say we're in scalar approximation, if you can talk about experiments. So we did not engage polarization properties, and this is another opportunity. Actually, polarization properties have been engaged in confocal microscopy with superoscillatory hotspots. But yes, this is another degree of freedom one can exploit, for definitely.
Thank you. Next question. Do you think that this technique might have applications for detection of fast gravitational waves, seeing as it deals with very small displacements?
Yes. Yes, I do. Yes, I do. I think that we actually, a few weeks ago, I have exactly this question, which came from a scientist working on gravitational wave detectors. And he didn't ask the question. He simply said, this technique can be used for gravitational waves. And he was very excited. We were in correspondence. So yes, I think that there's certainly a case to look into that.
Excellent. The next question, what limit to the pulse duration do you expect? That is, could you combine the picometer and the femtosecond?
There's a compromise here, of course, right? And the compromise is in spectral widths or spectrum of the radiation of short and ultra short pulses and coherences they have, and this put a limit on size of the local K vectors. But as in any compromise, you may find very interesting applications on the middle point of this compromise. And I need to say that we are looking at that right now for a particular type of light pulses.
Interesting. Thank you. A potentially related question. What is the limit on the speed of the imaging system? In other words, what is the frame rate of this system?
Yeah, very good. So with CW laser, the frame rate of the system is limited by only one thing. this is your frame rate of your camera, right? So so far, our experiments were done with conventional spectroscopic cameras, which have very limited frame rate, maybe up to 100 frames per second. But we just recently received a commercial camera, which can go to 100 kilohertz. And I am aware, do not have yet access to that, that there are cameras already which can go to 100 meg frame rate and actually 250 meg frame rate. So if you can put your hands to such a camera, this is your frame rate.
Understood. Thank you. Next question. Does the neural network that you're using introduce some additional knowledge in the reconstruction? If you were to reconstruct something really different from the training set, would you succeed?
Yeah, this is a classical question about application neural networks and fundamental science. Do they not generate knowledge we never thought about, which has no physical relationship? So they are, and this is always a concern. And so there are two sub-questions. The first sub-question: if you train network to recognize a slit, can it recognize a double slit? And the general answer is yes. There are many examples of that, but a second answer is, but you need to train it properly. But the second answer, for instance, in spectroscopy, they are quite routinely neural networks which pick up resonances from the spectrum and train it on a smaller number of resonances, say 5, 6 resonances. In fact, after proper training, they can provide access to a larger number of resonances. And I have a colleague who is doing that, exactly that, for nuclear magnetic resonance imaging. But the other question is, can the network invent something which does not exist? And the general answer, yes. And the sub-answer is there are many tricks in neural network community which help you to control that and stop that.
I think of it as the difference between interpolating results and extrapolating results. Oh,
yes, yes. So, yeah, so this is also a good question. So the neural network can work as a correlator. So you provided, say, a lot of data about slits, right? And then only thing you do is then correlate your test result with this database and pick up the closest component there, simply by calculating correlation coefficient. So this works, but but does not help in situation, for instance, when your position of your object, for instance, is not known. So, for instance, you throw your object into a field of view of the microscope, say, for instance, a sphere, but you don't know where it is. So then correlating against a library is not that efficient anymore. But if a proper neural network develop a deconvolution mechanism, it will still be doing this with similar accuracy as the object was placed in a fixed position. And this is perhaps the most treasured advantage of using neural networks rather than correlating with the library.
Thank you. I think that completes the question period. Thank you very much, Professor Zheludev, and I'll pass it on to Professor Corkum.
Yeah, thank you very much. Thank you for your attention.
Well, I want to thank you for a very interesting talk, Nikolay. It was many questions, and I think we filled up the full hour of your talk and probably consider somewhat more. So thank you again, and maybe I'll meet you at PQE.
Thank you for inviting me, and it was a great pleasure being here. Bye-bye.
Maybe we'll meet at PQE, we'll see.
Yeah.